All right, thanks everyone for joining us for another Live in San Francisco Authors at Google Talk. Today we have Anil Ananthaswamy talking about the edge of physics. He is a consultant, or was a consulting editor, still is, for New Scientist in London. He was a computer scientist, I believe, for software engineer for about 10 years. He's contributed to National Geographic News, very, very well educated in the field, but also extremely good at relating physics to the rest of us, basically. Prior to moving to London, Anil lived in Berkeley, so welcome him back to San Francisco.
Hi, everyone. Can you hear me clearly? It's a double pleasure for me to be here in the Bay Area. As Jesse said, I used to live here and work as a software engineer. So about 10 years ago, I moved on to write about science. And so it's kind of nice to come back and start speaking about this to people that I used to work with. Just to tell you a little bit about this presentation, I won't be reading from the book. I wanted to show you some slides of the various trips I made to write the book. And these trips were to some pretty remote parts of the Earth, from the Atacama Desert in Chile to Lake Baikal in Siberia in the winter, to Antarctica, to the South Pole. And before I start showing you the slides, I just wanted to sort of tell you how I came upon the idea for the book. For the longest time, I wanted to just travel to mountaintops and write about telescopes. And it was a very thin idea, and I don't think any publisher would have really liked it. And it sort of languished like that for a long time. And in about 2004, I became physics news editor for New Scientist in London. And as part of that, I came to Berkeley and Stanford to meet scientists just to get an idea of what's happening in physics so that I could do my job better. And it was one of these discussions with a cosmologist in Berkeley where at the end of the discussion with him, I mentioned to him that I would like to write about telescopes on mountaintops. And he planted the seed in my head, saying that, oh, you don't have to stop at mountaintops. You can literally go to the extremes of this planet where there are other experiments that are also important for physics and cosmology, if not more important. And that sort of set the whole thing in motion. And I realized I could tell the story of what's happening in physics and cosmology, but through the eyes of a traveler who's going around to these various places and talking about experiments rather than the theory. The theory is very integral to the book. It makes its presence felt all over the book. But the heart of the book is really about the experiments that are going to be necessary to start sort of answering some of the very big questions in physics. And I'll briefly mention some of the big questions in physics as we go along. So let me just move on then. The first chapter, the slides are that I'm presenting now, they're organized in a narrative that is as it is in the book. This is not the sequence in which I made the actual travels, but I think they work better if I stick to the order that I used in the book. So I started off in California at the Mount Wilson Observatory near Pasadena. And this is where in the early 1900s, Edwin Hubble discovered that the universe was expanding. So if you think back to the early 1900s, our conception of the universe was just the Milky Way. We had really no idea of whether there were any galaxies and if there was anything else outside the Milky Way. And Hubble was the first to really show conclusively that not only were there galaxies outside the Milky Way, but also that they were moving away from us in a very specific fashion. So this was, for me, a pilgrimage to a very old and venerable telescope just to see what it's like. So this is the view of, you see the dome of the 100-inch telescope. This is atop Mount Wilson. And you can see this from Pasadena on a clear day. I should confess this is not my picture because the day I landed up in Pasadena, it was completely cloudy and raining, and I couldn't see any of this from the outside. This is inside the dome. This is the 100-inch telescope that was actually used by Hubble to figure out the expansion of the universe. And what Hubble managed to do was that he figured out a relationship between the galaxies that are moving away from us and the distance that they lie from us. And if you work backwards in time using this relationship, this mathematical relationship that he came up with between velocity and distance, it became very obvious that there must have been a time in the past when all these galaxies were at one point. They were sort of speeding away from each other. And that was literally the thing that laid the foundation for the Big Bang theory. Apart from Einstein's equations of general relativity, this is where observational cosmology began. I just wanted to show you this particular galaxy. It's called the Sombrero Galaxy. It's a striking picture, and it is nothing like what people like Hubble would have seen. This is actually taken with a 4-meter class telescope in Chile. But the reason I bring this up is because even before Hubble did his work, there was an astronomer called Vesto Melvin Slipher, who in the early 1900s, using a telescope in Arizona, was beginning to understand that these galaxies were moving away from us. At the time, these were not even called galaxies. We didn't know what they were. They just looked like clouds in the sky. They were called nebulae. And he figured out that these nebulae were actually receding. And this particular one was receding at about 1,100 kilometers per second. And when Slipher mentioned this at a meeting of astronomers in 1914, everyone stood up and clapped because they realized that they were hearing something very momentous, but it wasn't clear what. What Slipher hadn't been able to do was figure out the distance to these galaxies. He just knew that they were moving away from us. And then Hubble came along and did many more observations, and with the much bigger telescope at his disposal, he was the one who figured out that these were moving away from us, and they were outside the Milky Way. And this is just to give credit to Slipher, who often goes unmentioned when we talk of the discovery of the expansion of the universe. This was, and it still is, the living quarters of the astronomers. It's called the monastery. George Hale, who founded the observatory in the early 1900s, was fascinated by monks and felt that his astronomers should live like monks and avoid any distractions. So he had a very sexist rule. He basically banned women astronomers from coming and working there because he thought that they would be a distraction to the men. Thankfully, by 1950s, that rule was abolished, and it's some very well-known women astronomers have worked there since. The man that you see was my guide. He's a 90-year-old man who actually was the son of a staff astronomer at Mount Wilson, and he essentially hobnobbed with Hubble, and so he was my living link to Hubble, which was quite a lovely thing. He's 90, and he still comes up almost every day as a volunteer guide to show people around. So let me just back up here a bit. So what happened was, by the 1930s, Los Angeles was getting really big, and light pollution was beginning to be a factor. And this observatory is actually not very far from the whole region. So George Hale, who built this one, figured that he needed to build a bigger telescope somewhere further inland, and he moved to a place called Mount Palomar, which is a much higher mountain and in a much darker region with far less light pollution at the time. It's already polluted now. But one of the things that happened in Mount Palomar in the 1930s was there was an astronomer, a Bulgarian-born astronomer called Fritz Zwicky, who started studying a cluster of galaxies in the Coma cluster. And he was looking at the speed at which these galaxies were moving around in the cluster. And those speeds are indicative of how much mass there is in the cluster. So the speeds can tell you the gravity of the cluster that's holding these galaxies together. And he figured out that by looking at these galaxies, that there must be much more matter in the galaxy cluster than was visible. So that was the beginnings of our understanding that in the universe there is something else apart from normal matter. Normal matter being the matter that we are used to, made of electrons, protons, neutrons, and the like. And he figured that there was some other kind of matter, something else that was providing the enormous gravity for these clusters that was holding these galaxies together. This was 1930s, late 1930s, and no one really paid attention to it because it was a fairly outrageous claim for its time. But then by the 1960s, people started actually making observations of nearby galaxies and started realizing that indeed what Zwicky had come up with was actually true. And that unseen aspect of the universe we now call dark matter. And my next trip was to an underground mine in northern Minnesota to see an experiment that is actually trying to detect dark matter. And the reason why it's called the experiment that detects nothing is not to demean the experiment, but it's basically the idea of the experiment is that it should be built in a way where all the noise that is present on Earth from cosmic rays, from ambient radioactivity, all sorts of things should be excluded from the experiment, in the sense that you should be able to filter out everything that can possibly create a false signal so that it detects nothing from the environment. And at that point, if you do see a signal, it will most likely be a dark matter particle. And I'll talk a little bit more about that. The reason why it's inside a mine is also because you have to protect yourself from all the sort of environmental noise on the surface. But before I show you slides of the mine itself, in the 1960s, this is the Andromeda Galaxy. This was a galaxy that was studied by an astronomer called Vera Rubin. She's in her 80s now, and I went to see her personally, and she was quite amazing. She talked about this galaxy as if she was observing it just yesterday. And one of the things she figured out was if you look at the galaxy, you'll see that there are a whole host of stars at the very center, and as you go further and further away, it gets sort of thinner, but there are stars all the way to the very edge. And if you just apply simple sort of Kepler's laws and Newton's laws to the motion of the stars in this galaxy, what should happen is that the stars at the very center should be moving really fast, and as you move away further to the periphery of the galaxy, the stars should start slowing down. It's just like in our solar system. You have Mercury moving very rapidly around the sun, and as you move further away, all the way to Pluto, Pluto actually moves at a very leisurely pace, and that's just simple Newtonian physics. When she observed the velocities of these stars, all the way to the very edge. In fact, they had a good enough instrument where they could go beyond the visible edge of the galaxy and just look at ionized hydrogen, so the hydrogen gas that's also part of the galaxy, and they found that everything was moving at almost the same speed, that there was no fall off in the speed of these stars as you moved away from the center. Something was wrong. And again, the only explanation is that there is some matter in this galaxy, and indeed in all galaxies, that outweighs the matter that you see, almost 10 to 1, and that's providing the gravity that is holding these stars together. If that wasn't there, the stars at the very edge would just fly off, and they wouldn't be there. The galaxy couldn't be held together. So this was the first serious piece of evidence, observational evidence, that the universe is made of a different kind of matter, or at least has a predominant component that is dark matter. And so this was a trip to the mine. It's about 4 hours drive from Minneapolis. And as luck would have it, I chose, I actually flew from San Francisco to Minneapolis, and it was very sunny in Minneapolis. I landed, it was very sunny in San Francisco. I landed in Minneapolis, and it turned out there was a blizzard on the way. So I literally had to race north, leaving the blizzard behind, which all added to the drama, helped in writing the book. So this is the head frame of the mine. This mine is an abandoned iron mine. It was built in the 1880s, and it lasted until 1960s. And it was a very, very good iron ore mine for the U.S. It was one of America's premier iron ore mines. And once it was abandoned, when it became too expensive to mine it, it was closed. But then physicists discovered it in about 2 decades ago, and they started building an underground laboratory, essentially for experiments which need to be shielded by cosmic rays on the surface of the Earth. You go underground, and so in this case, you go about half a mile underground using just this shaft. That's all there is. It's a cage that's been operating, since when the mine was functioning. And it takes 3 minutes in complete darkness. It's a rattling ride, and I have to confess, I was more than a little scared. And you come down to the bottom, the cage opens, and this is the sign that you see, 2,300 feet below the surface. And as you look to your left, as soon as you get out of the cage, is this thing called a drift tunnel. The drift tunnel is the tunnel that was dug in order to get the ore from sort of where the seams were. And we took a ride. This is a 3/4 mile long tunnel, and you go in all the way. And now there are lights, but at that time they would have been working without all these electric lights. And you can see these gigantic caverns that have been left behind by the miners. The caverns are, they can have ceilings up to 100 feet high or even more. And so this is inside one of the caverns. Our guide lit up this candle, shut off all the lights, and lit up this candle just to show the kind of light that the miners had to work with. This was it. This was the light which they worked for decades on end. And then, I told you, as you turn left, you go into the drift and to the caverns. If you turn right, you see this. And it's an extraordinary laboratory. It's called the Sudan Underground Laboratory. And there are 2 massive caverns that are in there. And you have to imagine there are tens of thousands of tons of material there. Each of those, every piece has to be brought down in literally cage-sized pieces, piece by piece. So even the design of the experiment has to be done so that you can actually dismantle it, put it in that cage, bring it down, and assemble it underground. And that particular experiment that you see at the far end is a neutrino detector, which is not what I went to see there, but it's quite an experience being down there. So this is the 2 people who are showing me around, one of the lab technicians and a physicist. We're about to step into the so-called radio frequency room. That's a room that has been electromagnetically isolated from everything else, and that's where the dark matter detector is placed. And you can see that we're dressing up as if we're going into a clean room. In fact, it's worse than going into a clean room. Even ambient radioactivity, your bodies are radioactive enough that the detector will pick it up. And so the detector itself is shielded in inches thick of lead, and lead itself has a radioactive isotope, lead-210, which decays. So in order to protect that sort of decaying lead from the detector, they have another layer of lead which was salvaged from ships that had sunk off the coast of Europe in 200 years ago. So most of that lead that is old lead, the radioactive isotopes have decayed, and they use that to shield the experiment from the new lead, and so on and so forth. It's a staggering thing. And my tape recorder, my camera, anything that I was taking in had to be wiped clean with alcohol, because even fingerprints, when you sweat, there's radioactive elements in your sweat, and if it shows up in a fingerprint, the detector will pick it up. So you can imagine how sensitive this detector is. So that's essentially what they're building, something that detects nothing. The detectors are crystals of germanium and silicon, about hockey puck-sized crystals that are put inside this copper tube. This copper tube is ultra pure. Lots of stories about how everything has to be pure enough that no amount of, they're essentially trying to negate any radioactivity in the vicinity. This thing is then cooled down to near absolute zero, and then shielded with all the layers of lead and stuff to prevent environmental noise. And the idea here is that dark matter is something that is supposedly filling up our galaxy. There's, like I said, 10 times more matter in the galaxy that is made of dark matter than normal matter. So what that means is Earth, as it's moving around in the solar system, and the solar system is moving through the periphery of the galaxy, we are plowing through a sea of these dark matter particles. And the hope is that, and by definition, dark matter does not interact with normal matter, which is why we don't see it. We can only discern its gravitational influence. But there is a way in which you can detect it if indeed it's made of dark matter particles. And that is if a particle were to hit the nucleus of, say, a germanium crystal or a germanium atom or a silicon atom. Now, so these detectors are cooled down to absolute zero, and they're hoping that when one of these particles hits their germanium crystal or silicon crystal, it's going to raise the temperature of that crystal by a few microkelvin, or it's going to induce vibrations in the crystal lattice. And you can imagine how sensitive that experiment has to be. So it's cooled down to near absolute zero, shielded by all these things, and that's what they're doing. They're watching for an impact from a dark matter particle. It's been going on for years, and they haven't seen any yet. but the experiments are getting bigger and more sensitive. So there's hope that maybe this year or the next year something might pop out. I don't know if you know, but in December there was a bit of a fuss about this particular experiment having detected 2 events. After they had done all their exclusions of environmental noise and all the statistical cuts that they need to do, they were left with 2 events that they couldn't explain. And they think it was dark matter. But it's not statistically significant enough. There's a 1 in 4 chance that it is still noise. And for particle physics, that's an absolute no-no. So no one claimed discovery, but at the same time, there was a considerable excitement because it's the closest they've come to actually seeing anything. Now, this experiment is trying to do what is called direct detection of dark matter. There are other ways in which you can detect dark matter, and the other obvious way is indirect detection. So if our galaxy is filled with these dark matter particles, they will assemble in regions of high gravity. So at the center of the Milky Way, there's a supermassive black hole, and the gravity obviously is really high out there, and dark matter particles tend to accumulate there. And when they are accumulated in very great numbers, they will collide with each other, and the properties of the particles, theoretically, are supposed to be such that if they collide, they will annihilate and create other particles that we can observe. And so there are experiments that are looking for these secondary particles that should be coming out of dark matter interactions. And I went to see another experiment. This was in Siberia. They have something called a Lake Baikal neutrino telescope. Neutrinos are subatomic particles that are very much like dark matter particles in the sense that they absolutely don't interact with normal matter in the way that you would think. If you stacked up a light year of lead, 1 light year thick stack of lead, and you fired a low energy neutrino at it, it'll probably go right through it. So the interactions are so little. But neutrinos are real particles. We know that they exist. We've detected them in copious numbers. So they're not sort of hypothetical particles like dark matter particles. And if dark matter is annihilating at the center of the galaxy, one of the things it should be doing is spewing out neutrinos. And so these neutrino telescopes are looking for this signal. And the way you would do it, because these neutrinos interact so faintly or so feebly with matter, what you need to do is essentially watch a very gigantic volume of some detector material. So then you have a statistical chance of sort of catching one of these neutrinos. So if a neutrino were to hit water or ice, it emits a blue light, something called a Cherenkov light. And the idea is if you can watch for this light, then you can reconstruct the energy of the neutrino, where it came from, and things like that. Where do you find such a big volume of water? And, well, Lake Baikal in Siberia is one such place. It's a lake that's 800 kilometers long, about 40, 50 kilometers wide in most parts, if not wider. It's more than a mile deep, and it's absolutely clear water. It's one of the most pristine lakes that you'll find in the world. And so that's where I went to see. That's the view of Lake Baikal from the coast of from the coast where the experiment offices were situated. Offices is a very loose term. I'll show you why. And you'll notice that this is a frozen lake. And when I called up the scientists saying, "Can I come and visit you?" they said, "Of course you can, but you have to come in winter." And this was Siberia in peak winter. And the reason why they do this is that the detectors are essentially things called photomultiplier tubes. Now, photomultiplier tubes are you can think of them as the opposite of television tubes. So in television tube, you supply electricity and you get out photons. In a photomultiplier tube, if it detects photons, it gives you an electrical signal. That's all, in very basic terms, that's what they are. So they've got these giant spheres of photomultiplier tubes that have been submerged about 1 kilometer deep into the lake. And they're essentially watching for a neutrino coming and hitting a molecule of water and trying to look for that blue light. There are about 228 of these photomultiplier tubes deep inside the lake. If you are working in summer or autumn or something like that, when the lake is not frozen, you would need ships and you would need submersibles to go down and wire these things. The Russians, unfortunately, have been working on a very tight budget, especially after the fall of the Soviet Union. The monies that have come in for them are very little. So they work in winter. They wait for the lake to completely freeze over, and then they use the lake surface as a platform. They set up their ice camp on top of the ice. They cut holes in the ice. They know where their detectors are underwater. They cut holes in the ice, and then essentially get their cranes and winches and get the instruments out. They have 2 months to do their work. Any repairing, any maintenance has to be done, and then they have to get out before the ice melts. So it's a pretty amazing operation. This particular picture, the line of black dots that you're seeing is the ice camp, and we're about 4 kilometers from that ice camp on the near shore. The far shore is 40 kilometers away, and so you can imagine the size of those mountains. That's 40 kilometers away. This is a picture of the Russians and some German physicists working on the ice. And I still can't believe that one guy, I remember being shocked by him. He was working bare-chested all day long. And those are you're standing on ice, 1 meter thick ice. And you can see the buoys that have been pulled out. These buoys are the ones that are at the very top of the detector. And so every winter they go there, cut a hole in the ice. A diver dives into frigid waters and essentially locates the buoy and gets it out, and then using that they haul out the entire so-called string of photomultiplier tubes. These are just long strings which are all the way sort of 1 kilometer underwater. And this is a picture of what the photomultiplier tubes look like. So pairs of these are essentially strung down into the water. And just a scene of how the lake looks there. This is the old Trans-Siberian Railway, which goes along that section of the lake. It's not used by the Trans-Siberian Railway anymore. Local trains sort of trundle past once a day, and they are the ones that bring in supplies. And the old railway buildings are the ones that are being used by the scientists for their living quarters. So when I said offices, that's what I meant. That this is one of their office buildings. It's probably 100-year-old railway building that's been converted into their control room. Very, very basic living conditions because they're working on extremely little money. You can imagine $20 million spent over 20 years. This kind of science experiment, if it's being done in Europe or in America, and there are experiments like this being done, they've already spent about 300 million in a few years, and these guys have spent 20 million in 20 years. And they are a pioneering telescope. They were the first to detect certain kinds of neutrinos using a natural body of water. This is our drinking water. Every morning we would go to the lake shore, dig a hole in the ice, get the Lake Baikal water into a bucket. And so you can imagine it was a lovely experience, a fairly rough experience. But then that's what they do every year. I was quite in awe of their abilities in terms of enduring this cold. So on the very last day, I was told by my German physicist host that since I had come there for an adventure, I should go sleep on the lake at night. And until then, I was sleeping on the shore. And I thought, well, that sounds very good. And then he mentioned that be prepared in the middle of the night to literally jump out of your sleeping bag, and if you're in your underwear, then just run out on the ice in your underwear. And I was really shocked. I didn't know what he meant. He said that the ice actually moves. It heaves, and in daytime you don't notice it because you're working, but if you're sleeping, and then you start thinking about it, there's a mile of water underneath. And this is a massive lake. It's not a lake, it's a sea. And there are waves, and the ice is constantly heaving, and it's very, very frightening, apparently. And as if that wasn't enough, he also told me, well, and there are earthquakes out here. And and by then I was not ready to go. I really was getting frightened. I didn't want to go and sleep on the ice. But a lot of things had been set in motion by then, and some person had given up his bed and he'd gone to sleep somewhere else. So I made it there, and there was a graduate student in one of those cabins who was sharing the cabin with me. And he welcomes me by saying, oh, don't worry, there are earthquakes here all the time. As if that was meant to reassure me that nothing happens, and didn't. And sort of I lay down on the bed, and the first thing that caught my attention was the sounds. There were these gunshot-like sounds, whips cracking or doors getting shut, and it was the ice cracking. So the ice is constantly moving and cracking underneath you. There's a mile of water underneath, and by then I was absolutely frightened. So I asked him, so how do you manage to sleep? He said, oh, as long as there are sounds, you don't have to worry. All that means is the ice is just protesting. It's when the sounds have gone, that means the cracks have opened up large enough that there is no sound anymore. That's when you need to get out of here. So suddenly the sounds were like a lullaby. I actually slept very peacefully. Anyway, this was an amazing experiment. From there on to see the Very Large Telescope in Chile. The Very Large Telescope, very interestingly named one. Astronomers, when it comes to naming telescopes, seem to have great imaginations. The next one in the line is called the Extremely Large Telescope, and apparently there's one more in the works which is going to be called the Overwhelmingly Large Telescope. So, but the reason I went to Chile is because the Atacama Desert. This is flying into Santiago, the Andes in the background. From there to a town called Antofagasta, and then a 2-hour drive to into the Atacama Desert, pretty high, place called Mount Paranal, which is at 9,000 feet. So this is just the road trip, and that's how the landscape looks. It's just absolutely dry. The Atacama Desert is pretty much the driest place on Earth. In some of these regions, especially near where the telescope is, it hasn't rained for decades. There's not a blade of grass, no sign of life. NASA uses this region to do their tests on their Mars rovers. And that's where they're building telescopes, and you might wonder why. Well, partly because it's dry. Water vapor is a terrible thing for telescopes because water vapor in the atmosphere absorbs light. And so you can imagine light that's been coming to us from a galaxy, say, 1 billion light years away. So it's traveled billions of years. And then in the last segment of its trip, about a few kilometers of the atmosphere can ruin that light. So the water vapor can absorb it, or the turbulent layers of the lower atmosphere can smudge the light. So essentially, what astronomers constantly try to do is get to very, very dry regions, and also to get high above the lower layers of the atmosphere, which is why you find them on mountaintops. There are other climatic conditions that are useful. On the shore of Chile, the coast of Chile, which is not very far from this place, there is a cold current called the Humboldt current that flows north along the coast, and that current pulls down the clouds. So there's an inversion layer of clouds that's created. So when you're standing up on the mountaintop, you don't see clouds on the top, you see clouds below you. And so essentially it leaves the mountaintop with about 300 days of clear skies, absolutely cloudless skies. So imagine you're flying in an airplane at 40,000 feet and you're looking down and you see clouds. Well, that's what you see here, except the clouds are down at 6,000 feet, and the summit of the mountain is above that. In that dry region, the astronomers have sort of built a residence where they stay. It's a subterranean, a part of it is underground. And when you step inside, this is what you see. It's one of the most amazing little places. It's very, very humid. They managed to sort of put a swimming pool in there to keep it humid, because if you're going to be working there for weeks, months on end, you need the humidity. And so this is the place where they stay. And right outside that's the mountain on which the telescopes have been built. You can barely see the domes at the top, and these are the 4 telescopes that make up the Very Large Telescope. So each telescope is a 8.2 meter primary mirror, and at the time that they were built, and even now, they're among the largest telescopes in existence, and especially 4 in such close proximity. There's nowhere else on Earth you'll find these such telescopes. You might recall the earthquake in Chile recently, and you would wonder why they would build such fancy equipment in places like Chile. Well, obviously the skies are wonderful, which is why they want to build them. But at the same time, you have to deal with earthquakes. And this mirror, this is one of the mirrors of the VLT. You can see that shiny bit. That's 8.2 meters across, and it's 18 centimeters thick. And the whole thing just the mirror weighs about 23 tons. And it's so heavy and relatively thin compared to its diameter that as the telescope is moving sort of from zenith to horizon and back and forth, the mirror is going to warp a bit because the gravitational forces acting on it change as it moves, it changes orientation. And that's enough to change the shape of the mirror, enough to mess up your observations. So actually, underneath the mirror, there are about 150 pistons that are constantly pulling and pushing at the mirror to keep it in shape. So essentially, the mirror is not anchored. It's floating on these pistons. So if an earthquake were to happen, it's going to just rattle around and break. There's nothing holding it. But the amazing thing is that you can't see it very clearly in this picture, but there are clamps all around the periphery of the mirror. And the moment they sense a tremor, these clamps hold on to the mirror, 23 tons of it, and just lift it right off the supports, and then anchor it to the superstructure. And then the superstructure is designed to just sway with the earthquake. So the idea then is that the mirror is not going to rattle around, and it's just going to, if the earthquake is not too severe, if it's severe enough to damage the superstructure, that's another thing. But for most earthquakes, this will work, and it has worked in the past. Let me just... so the reason I went to see the VLT was to understand... I mentioned dark matter. We don't understand what about 90% of the matter in the universe is made of. But about a decade ago, astronomers were looking at what are called supernovae, type 1 supernovae, which are just stars that are dying. And they were using these stars to figure out how the expansion of the universe has changed over time. Hubble found out that the universe is expanding since the Big Bang, and then the expectation among physicists was that this expansion should now be slowing down because the gravity of the matter in the universe should be starting to pull back the universe in a sense. So if you were to observe how the expansion rate is progressing in the recent past, say the last few billion years, the idea was that this expansion rate should be slowing down. And they found exactly the opposite, that in the last few billion years, the expansion of the universe, instead of slowing down, is actually speeding up. Something is blowing apart the universe. And that something, turns out, is the energy of space-time itself, that the vacuum of space, meaning everything, this, where we are standing, this is also a vacuum of space. In between galaxies, essentially all of the universe is contained in this vacuum of space. And that fabric of space-time has some energy. And when they total up how much energy that is, it turns out to be about 3/4 of the matter and energy in the universe. So this pie chart, now I can show this happily to a technology crowd without getting gasps. But that's our view of the universe now. We have dark energy, which is 73%. We have dark matter, which is about 23%, and normal matter 4%. So all our theories so far in physics, theories that have been verified and confirmed in experiments, can only vouch for 4% of the matter. The rest of the universe, 96% of the universe, is a mystery of sorts. We have theories, but we have really no experimental evidence to tell us what dark matter is. We don't really understand dark energy. There are many outstanding questions about where this energy of the fabric of space-time comes from. Has it changed over time? How will it affect the universe in the future? Things like that. And we really don't know. So the whole point of this book was essentially to visit various experiments that are going to start answering these questions. And so the big questions, what is dark matter? What is dark energy? I've just spoken about that. The other two big things is reconciling quantum mechanics with Einstein's general relativity. And quantum mechanics, we know, works really well. It's been verified endlessly by experiments, but it works at things at the microscopic level. And Einstein's general relativity, same thing. It's been verified really well, but it's a theory of gravity at cosmological scales, so for large distances. There are situations in physics where these two things have to be combined. Take the Big Bang. The Big Bang, the universe was supposed to have been smaller than a proton, if you can imagine that. But at the same time, all of the energy of the universe was compressed in that tiny volume, so it had extremes of gravity. So you need Einstein's relativity to deal with gravity, but you need quantum mechanics to deal with the microscopic volumes. And when you put these two together, they don't work. So you have two pillars of modern physics, relativity and quantum mechanics, that work brilliantly on their own, but in situations where you need to bring them together, they don't. And so there's this quest to find a theory of what's called quantum gravity. So I talk about that in the book. And then there's the physics beyond the standard model. I talked about how 4% of the universe can be explained, while most of that can be explained by this thing called the standard model of particle physics, which is essentially a theory of all the particles of matter, electrons, protons, neutrons, all of that, and the forces that act upon them, all except gravity. And it's a very well-tested theory, the standard model of particle physics. But we know that there has to be physics beyond that, because standard model cannot explain dark matter, for instance. It doesn't have much to say about dark energy. It cannot reconcile quantum mechanics with relativity. So we know that there is physics beyond it. So again, the experiments are beginning to provide us clues about that. Jesse.
So we could go on with yet another chapter, or we can leave that for those who still need to buy the book or those who've already got it. I was wondering if you wanted to open it up for Q&A for just a bit. We have about 10 or 15 minutes left.
I'll quickly run through probably Antarctica a little
Sure.
bit. Yeah, so people just a quick run through.
Sounds good.
So one of the most extreme places I went to was Antarctica. This is flying from New Zealand to McMurdo Station in Antarctica, the U.S. Base. This is the first sighting of the Antarctic, Southern Ocean outside Antarctica and the ice flows. This is landing in Antarctica. That's the plane. We landed on the Ross Ice Shelf, and you can imagine that gigantic plane. It's a C-17. It lands on the ice shelf. This is the Ross Ice Shelf, which is about 200 feet thick. It's about the size of France, and that is summer. And we were taken on a bus to the station, and the bus was called Ivan the Terrabus. Very nice bus. And this is just a view from the American base. Those are the Transantarctic Mountains at the back. And in the foreground, you can see a hut. I don't know if it's clear to you, but there is a small hut there. That's a hut that was built in 1902 by Robert Scott and his men when they first landed in Antarctica. And you can go into the hut and you can still see things like the last meal that was being cooked. And the clothes that they wear that have been left behind, the biscuit tins they brought with them from England on their ship. It's so cold that nothing has gone bad. Even the seal meat that they used, the seal that they killed, is lying outside. You could probably still eat it. This is a view of the American base from a hill just next to it called Observation Hill. And it actually resembles a little mining town. It's often been said that it reminds people of, I haven't been to Montana or Wyoming, but apparently there are mining towns that look like that. Just more views. There is a volcano right next door to McMurdo called Mount Erebus. This is the highest volcano, active volcano in the southern hemisphere, or it's the southernmost active volcano. It's 13,000 feet high, and it's active. It's spewing out gas and smoke and all that. But there are glaciers on the top, so you can imagine what kinds of extremes of nature exist in Antarctica. At the very top of that hill, from where I took these pictures, is a cross to commemorate, this is in memory of Robert Scott and his men. In 1911 and 12, they actually made it to the South Pole, but on their way back, they basically couldn't make it back to McMurdo, and they died in their tents about 150 miles away. So this cross is in memory of that. I was there to watch the launch of an experiment into the stratosphere. This is an experiment that is trying to look for antimatter. One of the big questions in cosmology and physics is, where did all the antimatter go? The universe, when it began, matter and antimatter should have been produced in equal quantities, and ideally they should have just annihilated each other, and all we should be left with is energy, except we have a universe made of ostensibly matter. So there are theories that suggest that there might be galaxies of antimatter out there, and this experiment was looking for one. And it is launched using something called a long-duration balloon. This is the balloon fabric being laid out on the ice shelf. And at the very far end, you'll see two trucks. They have 12 cylinders each of very, very highly compressed helium. And the balloon is being filled up with helium. It takes about an hour to fill it up. And the helium in the cold of Antarctica is compressed. It doesn't expand to its full volume. When the balloon actually reaches the upper stratosphere, about 40 kilometers altitude, the helium expands to 1 million cubic meters. 1 million cubic meters. You can imagine the size of that. The balloon is 400 feet across. It looks like half the size of a full moon when you look from the ground, if you can see it on a clear day, and you can. So this is the balloon just getting filled. It's an awesome sight. And that's pretty much how the setup looks. And when the helium has been filled, they release the balloon and it just takes off. Takes about 5 hours to get to the upper stratosphere, and in the upper stratosphere it just goes round and round the South Pole for 2 weeks. The experiment does its thing, and then they detonate an explosive, radio-controlled explosive. The balloon fabric flies away, and the payload parachutes down onto the ice. And recovering that is another story. We won't go into that, but they have to do all sorts of things to recover that. And then from there I went to the South Pole, but maybe we're out of time now. So happy to take questions, yeah.
Yes, first let's give Anil a round of applause. So we'll go into a brief Q&A. Unfortunately, we have to be out of this room in about 8 minutes or so.
Sure.
But if anybody would like autographs or questions afterwards, I'm sure I'll be willing to stick around. So if you have questions, please come up to the mic. I'll start off. We spoke briefly about how it's a fairly different type of physics book, if for no other reason, because it's typically someone involved in the experiment writing about it, and it's usually about a successful experiment. And this is about experiments that aren't failures, but they're certainly not solid successes just yet, per se. And you also talked about physicists having almost to be as passionate about setting up and executing the experiment as they are about eventually finding success in order to keep themselves going.
Yeah.
So, do you have any thoughts about why you approached it in this way? And did the scientists express any particular thoughts about how you were approaching it as well?
Well, the scientists I met who were experimentalists mostly. I mean, I did meet theorists, but they form a small section of the book. So the experimentalists were actually very, very happy because they don't get exposure normally. So all the physics books tend to be about the theorists and, and the big theories. So they were actually very pleased to be showing me around and showing me these experiments. The reason why I wanted to do it this way was just because I have a very soft spot for physics and cosmology in the sense that I think it is one of the loveliest sciences out there and has a profound effect on me. And I wanted to communicate that to people who normally would be put off by words like particle physics or theories and stuff like that. And this was a way in which to reach out to a far greater number of people by actually talking of the places and the people who do these experiments. So that's in terms of one angle for the book is just to broaden the scope of how you tell the stories in physics. The other thing also was to make a point that physics is actually in some sort of a crisis. As we saw, 96% of the universe, we haven't a clue. And the only way these theories are going to get verified are from experimental data. And we have a very big shortage of good experimental data at this point. And so this was a way of saying that this is the next generation of experiments that are going to hopefully lead us towards new physics.
Well, I've got a few questions. Or do you got one? Please come to the mic, though, so that we can get it recorded. Relatively simple question. How do these get funded?
Depends. Different agencies, like the South Pole stuff gets funded by the NSF mostly. In fact, most of the science in the South Pole is funded by the NSF. The balloon experiments, NASA has a big say in it. So the balloons are actually launched by NASA, and the individual researchers have to make proposals so that NASA can then carry their experiments up. The dark matter experiments, I'm sure there's federal funding, state funding, all sorts, because the experiment that I went to see is actually being done by physicists mostly based in Berkeley and Stanford. So I'm sure UC Berkeley, Stanford have a say in the funding, and NSF must have some.
Thank you.
Thanks for the talk, and especially for the pictures. I think that really makes some of these experiments come alive. And I was just thinking it would be a great candidate for either a documentary or a collection of photos to go along with the book. Have you looked into that?
Yeah, so I've put some pictures. I was asked that very thing many times, so I ended up putting pictures on a website, so just edgeoffphysics.com. So there are pictures out there. Documentaries, a couple of television people have approached, but television apparently is a very different business. So they say something and nothing happens for many years. So I'm not holding my breath on that. I don't know.
In dealing mostly with experimental physicists in the course of writing this book, did you get a good sense or any sense in general of sort of where they tended to stand with respect to some of the grand unification, theory of everything, string theory prospects for unifying physics? Or do they tend to just sort of compartmentalize themselves to their own spheres of study?
They tend to do both. Some, depending on who you talk to in a given experiment, some people are very compartmentalized. They are very focused on the experiment that they're doing. The problem with string theory and the theory of everything at this point is that they're very far from making predictions that can be experimentally tested. So I actually just focused on two things in the book that may help support string theory. One is the possible precise measurement of the curvature of space-time. There are certain models in string theory cosmology that predict that the curvature of space-time should be just a slight bit negative, as opposed to we think the universe is flat right now, but there's enough error in the measurement that it allows for a negative curvature. So that's one. It's not proof of string theory. It's just one of the possible things that string theory cosmology predicts. It's still disputed. Even that is disputed. The other big thing that actually would be a boost for string theory, again, not a proof, but a boost, is the detection of something called supersymmetry. I talked about physics beyond the standard model. And one of the physics that's beyond the standard model is called supersymmetry, which just says that every particle that we know of, electrons, quarks, gluons, everything, photons, all of them have a partner particle, a much heavier partner particle that existed in the early universe and has since decayed and gone away. We might be able to create that at the Large Hadron Collider. Now, if they create a supersymmetric particle and supersymmetric theories start getting verified, that would be a huge thing for string theory, because most string theory models require the universe to be supersymmetric. Again, it wouldn't constitute proof because the universe can be supersymmetric but not stringy. So,
all right. Well, and that wraps up the time we have. If there are any other questions, or if you'd like to chat about his book briefly, we'll be out in the lobby for a few more minutes. But again, thank you, Anil, and thanks for San Francisco.